Hear me okay? All right, good afternoon, everyone. My name is Stephen Tobe. I'm on the Parallel Computing Platform team at Microsoft. I am thrilled today to be talking with all of you. This is a topic that's really sort of near and dear to my heart, and I'm excited to share it all with you. For the next hour, we're going to be talking about parallelism, .NET 4 and Visual Studio 2010, and all the work Microsoft has done in this release to make parallelism easier. I won't go as far as to say easy, but I do think we've made some significant advances, and I hope you're going to like what you see. So we're going to do a very fast tour from sort of the bottom of the stack to the top of the stack, diving in certain areas. But I do want to take a few minutes up front to talk about why we're here. So just the general agenda, we're going to look at why parallelism, why now. We're going to talk a little bit about what's been done in the CLR itself, kind of in the bowels of the runtime to make parallelism significantly more efficient in .NET 4. We're going to walk our way up the stack, looking at a new namespace, several new namespaces, in fact, for writing parallel applications using tasks and some of the new concurrency primitives. We're going to move further up the stack, and we're going to look at parallel loops and parallel loop replacements. I'm not going to spend a lot of time talking about parallel link. Igor Ostrovsky has a talk on Thursday afternoon where he's going to do a 400-level deep dive into parallel link. If you're at all interested in link and parallelism, that'd be a great talk to attend. I am going to do just a couple demos of that. And then we're going to continue moving up the stack, and we're going to take a look at some of the new tools in Visual Studio 2010 for both debugging and profiling to really get a better sense for what your applications are doing and how they're working and fixing them to make them work better. Does that sound okay? Yeah? All right. Please, my style is very interactive, so if you have questions, yell them out. If I'm moving too slow, let me know. If I'm moving too fast, let me know that too. All right, just a little bit of a brief recap. By a show of hands, how many folks have heard of Moore's Law? Everyone. Excellent. And how many folks have heard that Moore's Law is dead? About half the room. OK, so I'm here to tell you that Moore's Law is not dead. It's just a little bit different. For those who didn't raise their hand initially, which was like 3 of you, just to recap, Gordon Moore, co-founder of Intel, back in the 60s and 70s, he made this what's now a relatively famous prediction around transistors and really the cost and the miniaturization of transistors, where, to paraphrase, he basically said that every 24 months, the number of transistors we'll be able to buy for a certain amount of money will double, and we'll basically be able to fit those transistors into the same amount of space. So if I buy a computer today, 2 years from now, it'll contain twice as many transistors in the same amount of space, and I'll pay about the same for it. Now, the hardware manufacturers have been able to do something really cool. They've been able to take this increase in transistor count, and they've been able to turn it into a similar exponential growth in CPU clock speed. And that's lasted for the last 20, 30 years, or at least up until about 4 or 5 years ago. At which point, things kind of leveled off. Again, by a show of hands, how many folks have a 20 gigahertz machine? One person. That's amazing. I didn't know they existed. All right, by show of hands, how many folks have a 4 gigahertz machine? Maybe 6. OK. So according to Moore's Law, and by analyst predictions several years back, by this year we should have had around 20 gigahertz machines. About 5 years ago, we had 4 gigahertz machines. Now, by a show of hands, how many folks have a machine somewhere in the 2 to 3 gigahertz range? Again, pretty much everyone except for the 6 people that raised their hands about the 4 gigahertz and the 1 person for the 20 gigahertz. So things have pretty much leveled off for a variety of reasons. CPU clock speed isn't the only thing that was increasing at an exponential rate. So was power consumption, heat dissipation, or heat needs. And we end up with power bricks like this weapon associated with my laptop sitting up here on the counter. So, as with any exponential curve, the hardware manufacturers have hit several walls, and they've been unable to take that exponential increase in transistor count, which actually is still increasing, and applying it to further and further growth in CPUs. Instead, we're seeing exponential growth in effect in the number of cores. So Justin Ratner, who is now one of the VPs at Intel, had this great quote back in 2007 where he said that Moore's Law scaling, this exponential increase in transistor count, should let us hit the 80 core mark in mainstream processors in the next 10 years. That's a phenomenal amount of computing power. You end up with machines that look kind of like this. This is real. This is a 128 core machine we have back in our lab in Redmond. It'd be nice if I had something like this on my desktop. I don't, although it would probably sound like an airplane taking off in my office if I had it. The problem is, when we get a beautiful machine like this, and we want to start taking advantage of it, well, if we take the applications we have today and we run them on this beautiful 128-core machine, we're going to be using just one of those little 128 boxes there. Everything else is going to be black, and depending on the optimism or pessimism level of the Windows developers who built Task Manager, our CPU usage meter will probably be somewhere between either 0 or 1%, based on whether they're rounding up or down. So we need to start writing our applications in a new way. Herb Sutter, who's an architect on the C++ team at Microsoft, he was also the chair of the C++ Standards Committee up until about a year ago, and I hear there's a chance he may become so again. He had this great paper back in 2005, which is, if you haven't read it, I strongly encourage you to do so. It's called The Free Lunch is Over. It was published in Dr. Dobbs' journal. And he basically calls, to paraphrase, I don't know if Herb's in the room, but to paraphrase, he basically calls all of us lazy. And he says that for the last 30 or 40 years, all of us as software developers have relied on this Moore's law scaling in CPU clock speed to get basically a free lunch of performance. Not fast enough today, no problem. We'll add new features, and in 2 years, when everyone goes out and buys new hardware, well, it'll be fast enough then. And 2 years after that, it'll be twice as fast, and all will be well. That's basically stopped. Now, if we want to regain that Moore's law as we get to 2 cores and 4 cores and 8 cores and 16 and 32 and 128, we need to start writing our application to take advantage of concurrency and parallelism, such that when we do get that beautiful 128-core machine, it'll just scale like we've been used to in the past. Now, obviously, this is very hard. It's not as easy as I make it sound. You can tell that by looking at the stack of software that Microsoft's been working on around parallel computing. This is not an easy picture. We've been investing a heck of a lot of effort to make this significantly easier. So what I have here, basically, everything we're doing around parallel computing, focusing on the stuff that's showing up at the PDC. One of the nice things about this as well for all of you is that if I overlay on top of this what all of our sessions this week are covering, we pretty much have full coverage for everything that's on this slide. So should be some very interesting material. So it is difficult, and we're trying to make it easier. One of the problems is the programming models that exist, or that have existed for writing parallel applications have been, well, not so friendly. So we want to shift over to models that are increasingly more friendly and that allow more and more developers to actually take advantage of parallelism. So as an example of this, I mentioned parallel link, which you can see on the slide showing up right here. I'm not going to talk about this in depth since Igor is on Thursday, but I will show a little demo just to get people excited about it. How many folks like Sudoku? Anyone? All right, maybe a quarter of the audience. So it's how I relax. I really like it. And so I decided I wasn't satisfied with just getting one per day in the paper. I wanted an application that would allow me to play Sudoku. So you can see I've got this application here, and I can select the level of puzzle that I want. And when I click one of these buttons, it's going off and it's actually generating a puzzle for me on demand, which I can then play. So that took about 6 seconds to render. And now I can go and I can play my puzzle, 1, or I'm just going to try out a bunch of numbers. All right, 9, play however I want. And eventually, eventually I win, and woohoo, all good. So at that point, I want to go and do another puzzle because I'm addicted. And again, I have to sit here and I have to wait for another 6 seconds. This is actually a fairly computationally intensive problem. I'd like to be able to parallelize this. So I'm going to go into my magic little game settings here and click on my magic Use Multiple Processors button. It's that easy. Click Start New Game. And now I can go to difficult. We can time this. 1, 2. So significantly faster to generate a new puzzle. Now, in the past, doing this sort of thing would require spinning up a whole bunch of threads, doing synchronization between threads, and so forth. This is what the code looks like. Here's the sequential code. This is using link. So basically, the way the algorithm works is I can only guarantee that a puzzle is no more difficult than a certain level, but I can't guarantee a minimum level of difficulty. So I generate a whole bunch of puzzles, and then I pick that with that kind of max bound set, and then I pick the most difficult one out of all of them to try and get up to kind of a small region. So I'm taking basically a range here from 0 to number of puzzles that I care about. This is something like 50 or 100. I'm going to, for each one of these, generate one puzzle. And then I'm going to use the aggregate method in link to basically select out the puzzle that was the hardest out of all of these. To parallelize this, I added as parallel. So basically, I just copied this code, pasted it here, and added it as parallel, which, as you can see, potentially in the IntelliSense comments, enables parallelization of a query. So this is what we call parallel link. And this is all about raising the abstraction. So you write your code using link to say what you want done rather than how you want it done. And we're able to automatically then replumb the system to re-implement the how to be parallelized. This is really sort of the long-term vision where all of these programming models will head, where you only express your intent. You don't have to deal with sort of how things are happening, and the system will take care of it for you. As another brief example of p-link, just because it's kind of fun, I was asked to do a talk about a year ago, actually, for some internal developers at Microsoft, and I was told to make parallelism fun. And I wasn't sure, it's already fun. How could it not be fun? But I needed to come up with something fun, so this is what I came up with. How many folks have heard of the infinite monkey theorem? All right, a small portion of the audience, maybe 10%. So the infinite monkey theorem you may know better by its actual description. The infinite monkey theorem is you put enough monkeys in a room with a bunch of typewriters, and eventually they're just banging away randomly. One of them is likely to type out the complete works of William Shakespeare. That's the infinite monkey theorem. So I've changed that around slightly to make it more computer science-y, to make it more of a genetic algorithm. I've got, here's my Shakespearean monkey. This is my skills with Office clip art. I was kind of surprised I could find a skull in Office clip art, but nevertheless. So here's the premise. You put a bunch of monkeys in a room. They're all a little randy. And they breed. And they just breed and breed and breed and breed and breed, generation after generation. And when monkeys are born, they're born knowing how to type a particular string of text. And every time you put them in front of that typewriter, they're going to type out that same text. And when this text is actually a genetic trait. So when the two monkeys breed, their little monkey pops out, and that monkey knows how to type a string that's some combination of its parent strings, potentially with some mutations that came in from the environment, just because the environment likes to do that. So we're going to run this, and we're going to see over time these monkeys kind of through Darwinian evolution and survival of the fittest. Only the monkeys that are better and better at speaking Shakespeare, in this case Hamlet, are going to survive and go on to breed and so forth. And so over time, you can kind of see them starting. This is the best monkey over here on the left. You can kind of see him starting to do something kind of like. We have do be. Oh, there we go. To be. Oh, the good. Yeah, so we can see we're getting about 24 generations of monkeys per second. This is going to take a while, so I'm going to stop that. And again, we have our magic parallel button here. This magic parallel button is implemented. If I go down to Shakespearean monkeys and scroll down. Again, we've got a link query here. This is the sequential. And I just changed enumerable to be parallel enumerable. Instead of adding as parallel, it's basically the same thing. Basically say use link, use parallel link. That's the only change. And now when I run this, instead of 24 generations per second, you can see they're going much faster and doing much better, and we're getting almost 80 generations per second. So almost a 4x speed up in terms of how fast these monkeys are able to breed. So very simple changes to the code for significant improvements. All right. I like to think of parallelism and the difficulties with parallelism as being all about overheads. Everything has a cost. And unfortunately, that's also true with parallel computing. So for example, if I just wanted to put some work into a queue for some background threads to pick up, there's a cost to putting things into a queue. There's a cost to taking them out of a queue. There's a cost to creating the delegate that represents the work. There are all these costs. Typically, for each piece of work, there are fixed overhead. So there are these overheads of execution, and then there are these overheads of concepts, of conceptual overheads. And we're really trying to address both of these. So from the bottom of the stack, we're going to focus on execution efficiency and addressing the overheads of execution. And we're going to work our way up the stack with addressing the overheads of concepts like we just saw with p-link. So I'm going to put forth a little argument here about why this is actually important. Imagine you have a piece of work, just one piece of work. And I want to process this on my 80-core box. Well, if I just have one piece of work, a piece of code that's going to run that piece of work, at best I'm going to be using one CPU because it's single-threaded. So in order to process this on multiple cores, I need to actually split up this work into multiple pieces so that I can process each of these pieces on a different core. Now, I mentioned we have overheads. Typically, this overhead ends up being somewhat constant, at least a portion of it, per piece of work. So I had some overhead associated with my big piece of work, and now I have that same overhead replicated 4 times for each of these divisions. Now, unfortunately, on that 80-core box, if I run this divided piece of work, yeah, I'm going to get a 4x improvement, potentially, but I'm not going to get an 80x improvement because I'm only at best utilizing 4 cores. And 76 of them are just sitting around twiddling their thumbs. So I need to further divide. So I need to divide and divide and divide. Now I end up with very, very small chunks. Each of these chunks has that same overhead. And now you can see the ratio of the blue to the green starting to get more and more significant. And as I decrease the size of my work items to allow me to split more and more and more, the overhead starts getting greater and greater and greater. And thus, to actually efficiently parallelize, I also need to parallelize. I need to be careful not to say paralyze, which can sometimes be the case. We need to actually decrease the overheads as well. And this is all about decreasing these execution overheads such that the ratio between the overheads and the actual work gets back into a sane territory so that I can actually continue to divide and saturate all of the available cores that I have. And that's really what the work we've done in the .NET 4 thread pool is all about. So to level set, I'm going to describe briefly the concepts behind the .NET 3.5 thread pool, which are very similar to thread pools in other systems as well. So basic idea behind a thread pool is you've got threads managed by the system. And this is because threads are relatively expensive. They're expensive to create. They're expensive to destroy. They're expensive to have too many. They're expensive to tear down. They're expensive to switch between, and so forth. As a result, we want to minimize the number of threads we have while still maximizing the amount of work that we're getting done. And this is what a thread pool is all about. It's about amortizing the cost of all the work that you're doing over a low number of threads that are managed by the pool implementation. So here in the .NET pool, maybe we've got, I should say, thread 1 through thread n. Ignore that thread 1 at the end there. We've got some number of threads, say 4 on a quad-core system, or maybe 8 on a quad-core system, whatever the system thinks is appropriate. We've got a queue of work. And as we create work items, for example, with thread pool queues or work item, these work items go into this global queue, and then the workers get all excited, you know, woohoo, I've got work to do. I have a purpose in life. They pull off that work, and they start processing it. Meanwhile, the queue might be filling up with additional items. In fact, these workers may themselves be generating additional work, which is going to go back into this global queue. And then when they finally finish some work, they're going to go back to the queue and grab some more. So worker thread, the last worker thread might complete and pull off another work item. More work might come in. And this sort of continues ad infinitum as long as there's work in the system. Now, this is great, except that there are some overheads here. If we're only dealing with a few processors, and thus with a few threads, maybe not that big a deal. However, as we start adding more and more and more cores, and we start dividing our work up more and more and more into smaller and smaller pieces, each of these threads needs to start going back to that global queue much more frequently. And you have more threads going back to the queue, which means you have much more contention. And contention is the bane of scalability. You want to avoid synchronization as much as possible, and this is a prime example of a synchronization point. Anytime you have communication, you're ending up for a world of hurt when it comes to scalability. You can think of this in terms of teams. You know, if you're just one person, you might not be able to get as much done as 2 people, but you're going to be very efficient. You start adding another person to your project, now you have to communicate. There's some overhead for that communication. You have to sync up. You're both going to be fairly efficient, but you know, there's going to be some overhead to it. You start adding more and more people, now you need more and more team meetings. Those team meetings may not be all that efficient, so you need more meetings. Never happens at Microsoft, by the way. And so there are these overheads that show up in computer systems as well. There are other overheads which we will talk about when we look at the .NET 4 thread pool. So you're going to notice a few changes when I move to the next slide. I'll call some of them out. There are some words that changed here, and there are some pictures that were added up here, and then there were some words that changed down there too. So we'll take them in order. First, we have this lock-free global queue. So this was some really cool work that was done by a developer on the CLR team. His name is Eric, to make the throughput of the system significantly more efficient. He basically took the queue in the .NET 3.5 thread pool, which was basically a queue of T, protected by a lock, a monitor. And he kind of analyzed that and saw that as you add more and more threads, there was a significant amount of contention on that lock. So he replaced it with what's called a lock-free queue. A lock-free queue is built on top of the same lower-level hardware-provided primitives that locks are built on top of, interlocked operations. But they allow for, in certain cases, some significantly better throughput, significantly less less overheads associated than there is associated with locks. So he ripped out the old queue, he put in this new one with its lock-free implementation, and we saw significant improvements in throughput just from that one change, especially for very small work items. Now, another theme that I'll refer to later on is as we were doing this work with .NET 4, we found ourselves building these data structures for internal use a lot, a concurrent queue, a concurrent dictionary, a concurrent stack, some lazy initialization primitives, support for producer-consumer, for barriers for doing work in lockstep. We were building all these things internally, and we thought to ourselves, this is silly. We're doing all this work to create these reusable data structures internally. Shouldn't other people have access to them? So we cleaned them up. We gave them really nice APIs, hopefully, you tell us, and we made them public. And this queue is an example of that. So there's the new system.collections.concurrent namespace in .NET 4, which contains a concurrent queue, which is basically this lock-free implementation of a queue, which you can use in your own .NET 4-based applications. So let's say we start putting work into this system. So we've got work coming in, and it's going into this queue just like before. And again, these worker threads get all excited. And I'm not going to jump up and down again, but they pull off work, and they start processing it. And again, they might generate some additional work. But now here's where these local queues come into play. When they generate their own work, rather than that work going back into the global queue, the work starts going into the local queues. And again, one of the main advantages here is around decreasing a key synchronization point, a D point of contention, that of the global queue. So now, if multiple threads are pushing work into their own queue, no one is having to synchronize with each other, no one's having to go back to the global queue, and we're minimizing that contention point. There's another advantage here, and that is when worker thread 1 finishes its work, and it goes and it pulls out, it wants to go searching for work, it actually first checks its local queue, and it pulls out some work from there. Now the queue, the local work stealing queue here, that might be a bit of a misnomer. This is sort of a queue and a stack. In fact, when worker thread 1 here pulls out work, it pulls it out in LIFO order. It pops the most recent element that it pushed in. And this is for a very good reason, well, a few very good reasons, one of which is around cache locality. In modern architectures, accessing main memory is relatively inefficient. It can be a few hundred cycles or even potentially a few thousand cycles to get off to main memory. So the hardware manufacturers have done something very smart. They've introduced a level of caching, just like you might have in a web application, caching to prevent hitting the database multiple times. They've added in caches between the core and main memory, typically several levels. You might hear this referred to as L1, L2, L3, level 1, level 2, level 3, and so forth. This machine here has a bunch of level 1 cache and a bunch of level 2 cache. I don't believe it has any L3. L1 might take 1 to 2 cycles to access. L3 might take, let's say, 20 cycles, 100 cycles, something like that. Or L2. L3 might take 100 or 200, and then main memory is beyond that. So ideally, threads will access data that's in their cache. When we pull data out from memory, it gets cached locally, and then hopefully you touch your cache more than having to go back to main memory. And this is cache locality, basically staying local to your caches, saving the cost of all those trips. Now, in this example, I'm going to back up just a couple. When task 2 created task 5, there's a good chance that the data that task 5 was meant to process is hot in the cache, meaning it's existing in the L1 or L2. So now when task 2 is done and it wants to go pull off some work, if it pulls off task 5, there's a good chance that it's still hot in the cache, and so it's going to be able to run that task more efficiently because it's going to be able to make fewer trips to main memory. Always a good thing. So now let's say worker thread 1, or worker thread P rather, finishes task 1, and it goes in search of additional work. So as I said, it's going to check its local queue. It's not going to find anything there. So it's going to check the global queue, and unfortunately, it's not going to find anything there. And now it's going to go talk to its friends. So it finally has to go synchronize with its other threads. It goes and looks at thread 1 and says, I see you have some work. I'm going to steal it. Now, this is actually a good steal. This isn't a bad steal. It's going to pull off task 3. And this is kind of the queue side of the stack. Now again, task 3, it took task 3 for a few reasons. One is this locality example, or locality reason. Just like task 5 was likely hot in the cache, task 3 was the oldest thing, so it's likely cold in the cache, and so there's going to have to be minimal synchronization or minimal movement of cache lines between the various cores that are processing these threads. There's another good reason for this, though, and that is if worker thread 1 had generated a whole lot of tasks, that queue is likely kind of big, And now we have two different points at which the threads are accessing. Worker thread 1 is always accessing from the bottom. The other threads are always accessing from the top. And now we're minimizing the synchronization between all of these threads. So again, this whole system was engineered from the perspective of minimizing synchronization. And as we get bigger and bigger systems, this actually starts making a noticeable difference. There's one other really interesting thing that was done in the thread pool for .NET 4, which isn't just good for kind of parallel workloads, but also for massively concurrent workloads, where you just have a whole bunch of requests coming in that are all independent, very much like ASP.NET, where the thread pool serves as the main execution environment for ASP.NET. The idea here is something called hill climbing, where there's a heuristic that's constantly running in the thread pool to evaluate what the optimal number of threads should be. There's sort of common wisdom that says the optimal number of threads in a pool should be exactly the number of cores. That would be true if every thread was doing CPU-bound work all the time. But that's not the case. Threads do I/O. They read from disk. They read from the network. Especially in a situation like ASP.NET. They even go off and access main memory and may have to stall for a few hundred cycles while pulling down some data. So the optimal number of threads is typically something more than the number of cores and often varies over time as the workloads change. So this heuristic is now constantly running in the thread pool, and it tries to minimize the number of threads while maximizing the work item throughput. And so it keeps track of how many work items are completing and constantly tries to add and remove threads to get to a sweet spot on a hill where the top of the hill is the sweet spot. So some really cool work done in the thread pool for .NET 4. Any questions on that? Yeah.
You talked about taking it from the bottom one and pulling it from the top. What kind of lock
So the question is around the efficiency of accessing various sides of the work stealing queue. One of the cool things about this algorithm, and I should mention this, the general algorithm of work stealing isn't something that we came up with. It's actually being adopted by all the major frameworks these days, whether it's Intel's threading building blocks or Silk++ or Java 7. They all sort of recognize this to be a good strategy. One of the great things about this is that the local thread that's accessing its own side has to do very little synchronization in order to do that, assuming there's enough items in the queue. If there's very few items, it still has to basically take a lock. But if there are enough, it can use just a couple interlocked operations, maybe one interlocked operation. In some cases, it might not even need any in order to access from its side. Now, it is fairly expensive to take from the other side. Threads do have to take a lock, and so there is a significant synchronization point there. But for algorithms for which work stealing is very good, typical recursive divide and conquer, you're processing an XML document or a tree or a quicksort, anything where work produces more work. Once the system is saturated, it's very unlikely that threads are going to be stealing from each other. So that extra cost is minimized. And as an example of that, this highlights one more reason why, I should have mentioned, why it's good for task 3 to be pulled off by worker thread P. And that is, in one of these recursive divide and conquer situations, typically the older tasks or the older work items are ones that are going to produce more work. If you think about this in terms of a giant tree where you have nodes and children and so forth, task 3 might be the root, and then it spins off 4 and 5 to process these children, and 6 and 7 to process these, and so forth. If I were to steal 6 or 7, I'm closer towards the leaves, and thus there's less of a chance that they're going to produce more work. But 3 is towards the root, so there's a very good chance it's going to produce all this work off to the side. And so when worker thread P executes task 3, it then produces work which goes into its own local queue, and now they can just party on without synchronizing between each other. So pretty cool. Did that answer the question? Great. Yes?
Just going back to your previous example, why is that you're saying that you should exclusively use parallel? Why can't the framework automatically use parallel with that node?
It's a great question. The question is, why can't the system automatically parallelize? Some systems can to some extent. So, for example, Intel's compiler has some limited auto-vectorization capabilities. And when you give it a problem that it knows about, it does great. The problem is that for general languages without many constraints like C#, C++, VB, and so forth, it becomes pretty much intractable in most situations for a compiler to determine what's parallelizable and what's not. And one of the key reasons is pointers, references. If I give you two things and I say, I want you to write to each of these things, you don't know necessarily whether they're the same or not. And it becomes very difficult then to figure out whether you're stomping on, you need synchronization or not, whether it's parallelizable or not. That's a very quick tour through it. This is a problem that's been in academia for years and years and years, and while we are making some progress, it will likely continue to be in academia for years and years and years.
So, going back to your example of link, because it's a simple link statement, so do we need to know when to call? It's basically, we need to make the call, okay, you use parallel here, don't use.
Right, the follow-up comment was, going back to the link example, you need to basically opt in to say when you want to parallelize. And that's exactly why we've made it this as parallel. We actually initially went down the route of just changing all queries, but that can lead to some significant problems. And so we basically forced you to say, yes, this is safe to do, and yes, I know I will get speedups here, so I want to opt into parallelism. Sir? Yep. That's correct.
Why doesn't thread 1 need to take a lock when it needs to take something out of the queue?
So the question was, why doesn't worker thread 1 need to take a lock, even though other threads may need to access this queue? If worker thread 1 was accessing from the same side of the queue that everyone else does, it would. However, the intricacies of the work stealing algorithm, and there are very good papers on this, which I encourage you to go read if you're interested. It's a lock-free algorithm that basically allows, in many cases, in the worst case, worker thread 1 does have to take a lock. In the typical case, it has to use basically one interlocked operation. And in the best case, it might not have to use anything. Although, and that's true for our concurrency runtime in native. On the managed side, I'm pretty sure the worst case, or the best case is we still need at least one interlocked operation. All right. So we sort of covered execution efficiency, and now I want to move up the stack and spend some time talking about one of my favorite additions to .NET 4, which is the new task type. How many folks have used the .NET Thread Pool before? All right, maybe 3/4 of the room. So queues or work item on the thread pool is really good for fire and forget operations. You take a delegate, you push it into the thread pool, it goes off into the void, and one of those threads in the background processes it. However, it's often the case that we want to do additional stuff. We might want to wait for this work to complete. We might want to cancel it. We might want to do something when it's done. We might want to take a whole bunch of operations that we queued up to the thread pool and do something when all of them are done. We want to deal with exceptions. We want to be able to flow data between operations. We want to be able to debug this stuff. See what was scheduled into the thread pool that hasn't run yet. Thread pool queues work item doesn't provide any of that. However, the new task class does. So let's jump into some code. I've got here a Scratch project. So we have thread pool queues or work item. I can say thread pool queues or work item, and I give this guy a delegate, and it runs some work. Simple enough. As I mentioned, you can't do anything really more with queues or work item. It gives you back a Boolean, which, as far as I know, will never return false. You're right. So we've added this new API that's in the system-threading.tasks namespace. The core type is a task. I can say task factory start new, and just to use the same syntax, I'll say delegate. And again, I give it a delegate with some work to do here. The difference, however, is that I actually get back something from this call to start new. Now I get back a task, which we can see represents an asynchronous operation. Now that I have this task, at some point later, I could say, I want to wait for this thing to complete. Or I could say, when this is done, I want you to do something else. So I want you to continue with some other operation. I'll use delegate again. And do this when T is done. Now, you might ask yourself, why isn't this just an event? I register an event handler or something where I get a callback. Well, one of the main reasons is because we actually can give you back a task that represents this continuation. So now you can start chaining these things together. You can say .continue with, .continue with, .continue with, and so forth, and build up these graphs of tasks representing dependencies between tasks. You can also return data from tasks. So I'm going to change this to say var, taking advantage of the C# compiler's capability of doing type inference. And I'm going to return some data now. So I'm going to say, when this is done, do something compute intensive. and return the answer to everything in the universe. And now I get back a task of tResult, where tResult is an int 32, because I'm returning 42. If I were to say return Stephen, now this is a task string. And at some point later, I can say, what was your result? T2.result. And I get back the result of that asynchronous operation, where the system is handling all the synchronization. Yes?
Say if you're doing something compute intensive and you got to the T2.result, would it block until it happens?
So the question is, to paraphrase, what happens when I get to T2.result if T2 hasn't completed? And the answer is we will not make forward progress beyond the call to T2.result until it has completed, so that you can write this without having to worry about the synchronization, and it's taken care of under the covers, basically commingling the data with the synchronization. Now, the reason I didn't use the word block is because we can actually do some intelligent things here. If the work is currently running, then yeah, we have to block, or at least spin a little bit and then block. However, if it hasn't started yet, we actually potentially have the capability to reach into the scheduler's queues, pull out the work item, and run it right here, rather than blocking, waiting for some thread in the future to process that work item. So we can actually use the current thread to do useful work. And this actually brings up a good example, or I can bring up a good example of why this is important. Let's say I've got a tree type, where on tree, standard tree, I've got a left and a right child and some data. I might want to implement a method that walks over this tree. So if I were using the thread pool to do that, I might write something like this. I'm going to check first if the root is null, and I'll just return. So I've kind of reached a leaf. And now I want to spin up several items on the thread pool in order to process the children. So I'll say thread pool queues or work item, give it a delegate. This delegate is going to call walk tree to recursively process the left side of the tree and run the action. And then when it's done, it's also going to signal to this countdown event to say, I'm done my piece of work. I'm going to do this twice, once for the right side of the tree and once for the left. And then I'm also going to just run the action on the current data. And then I'm going to block the current call until both of the children have finished. So I'm asynchronously spawning both the left and the right-hand side. I'm signaling to this countdown event such that once it reaches 0, the main thread will wake up. And I'm hoping that with this code, I'm going to be able to process a large tree. So let's say I have a tree here. I'm going to say create tree of depth 12. And this is going to give me back a tree of int. And now I want to walk this. So I'll say walk tree, passing in the tree. And I'll give it very simple work to do. I'll just say console.writeLine, printing out the data from that node. So now I'm going to compile this. And theoretically, it should run very quickly. Unfortunately, not so much. So I'm going to bring up Task Manager and take a look at what might be going on here. And here's my application. And if I zoom in here, you notice this little number here? This is the threads column. I'm going to have to stop this before it kills my box. But basically, what's happening is we're blocking every single thread in the thread pool. As the thread pool is trying to process this tree, we spin up a thread, or basically we spin up a work item to process 2 children. It launches those asynchronous children. It runs the process for the current one, and then it blocks, waiting for those children to complete. So in effect, every work item I queue up is going to block a thread. So that's not ideal. In order to write this in a better way, where we can take advantage of tasks, so I'm going to get rid of all, I'll just comment this out. And I'll say, first I want a task to process the left side of the tree. So I'll say task factory start new. And this is going to do walk tree root.left action. We'll do the same for the right-hand side of the tree. Right. And now I can say process the current node, root.data, and wait all on the left and the right. So now if I run this, it should run significantly faster. The console.writeLine is taking a lock, so that's what's causing some of this slowdown. I'm also running in debug with the debugger attached. If I were to run without it, it runs significantly faster. The reason for this is because when we call wait all, we're able to basically, if the child tasks haven't started, rather than just blocking, we can reach into the thread pool's queues, pull out the work item, pull out the tasks, and just wait on and run them on the current thread rather than waiting for another thread to pick it up. Sir?
If you had done this one with threads, it would have run almost as fast as this one, or?
So the question is, if I had done this with threads, would it have run almost as fast? Potentially. I'd be creating several thousand threads, each of which by default would have a megabyte worth of stack. So on 32-bit, I would have blown out my virtual memory space. Not ideal. I would have also been taking up a significant amount of paging and all that kind of stuff. The bigger and bigger this thing gets, the less likely it would be true, because as we have more and more threads, the more context switching there is. Windows is pretty good at doing fair scheduling between threads, up to a point. Yeah. The question is, does task have its own thread pool? Yes and no. Does what have its own thread pool? P-Link. So by default, both P-Link and tasks are built on top of the CLR thread pool. These are actually built on top of a type called task scheduler. And task scheduler.default is the .NET thread pool, taking advantage of all the great work that was done in the CLR. That's correct. And that's, in fact, the main reason that we switched from our CTPs, our community technology previews, where we were building on top of our own scheduler. We worked with the CLR team to take a lot of that technology, build it into the CLR, such that whether you're using ASP.NET or P-Link or TPL or directly queues or work item or callbacks that use the thread pool, they're all going against the same shared source of threads that the thread pool can manage. Now, I said by default, and you can see that there's the word default here. Anytime someone says default, there's usually a non-default. So you can actually take advantage of other schedulers. We ship 2 in the box. One of them is the one that sits on top of the thread pool or integrated with the thread pool. The other is one that runs on the UI. So you can actually schedule tasks to run on the UI, which is useful in a situation where, let's say I said, let's pretend I'm in a Windows Forms application or Windows Presentation Foundation. I could launch some work. This work is going to go off and run in the background. And I'm going to do something intensive and return a value. Then I can continue from this work, taking the previous task that completed. So what I'm passed here is the previous task of int, my antecedent. And I could take its result and do something with it. So let's say we have t.result here. Yep. And then let's say I was in a Windows Forms app and I had a text box. So I could say label.text or .value or whatever it is equals result.toString. Now, if I were to actually run this in Windows Forms, that would be bad because this is running in the background, and you shouldn't access the UI thread from background threads, or UI controls from the background thread. So I can take advantage of the built-in scheduler that targets a current synchronization context, which think of this as meaning that targets the UI. And now when I run this task for this continuation will run on the UI thread. So I can very easily kind of go back and forth between various contexts based on schedulers. Sir? So the question is, has there been any significant progress around avoiding all that boilerplate we have to write to ensure that we are marshaling work to the UI thread? No. I mean, we've tried to make it easier with things like this, but the core Windows model of the UI controls must only be accessed by the thread that created them still exists. And so we're trying to make it, with this, easier to get back to that right thread. That limitation is still there. So the question is, if I could paraphrase, how do I know that I haven't messed up in terms of where I'm running my tasks, or my work? Maybe I'm running it on the UI by accident. I'm going to hold off on that question for about 10 minutes until I get to the tooling support. And if I haven't answered it then we'll talk. All right. So really cool stuff you can do with tasks. You can say, I'm just going to create a bunch of these guys. Let's say I have T1, T2, T3. I mentioned coordination. So if I had a bunch of tasks, I can say when all these things are done, I want to continue when all. So I can pass in T1, T2, T3. I get a reference to all of those tasks as an array. And now I can do something when all of that work was completed. So you can build up these graphs again, and just like with the continue with we saw, we can pass data through.
This will look like quite a lot of the stuff that's in the CCR, the coordination runtime. Is any of that stuff being used in
So the question was around the CCR, which is the Concurrency and Coordination Runtime from the Microsoft Robotics Studio. CCR does not exist in .NET 4. I like to think of the CCR and the task power library as being relatively orthogonal models, where there is some overlap in terms of things that you could build with the CCR and that you could build with TPL. However, I think TPL is geared more towards sort of proactive parallelism, where you know the body of work that's going to be processed, you express your dependencies in a very concise way, you do parallel loops and so forth, and you fan that out, whereas the CCR is more sort of a queued reactive model. Again, the core primitives are all there. This is all built on top of .NET, so you can do pretty much anything with either, but there are certain problems where one is better than the other. And this is actually a good point to make, that I don't believe in any way that TPL or Parallel Link or the CCR, that any one of them is the one programming model for parallelism to rule them all. Just as with languages, languages have different strengths for processing different types of problems. The same thing exists here. And it still remains to be seen what we'll actually do with the CCR longer term. But it's the core concepts of these queues with operations that operate on those queues is sort of a foundational model in message passing. And it's definitely something we're interested in. In fact, if you go to the talk on Axum on Thursday, which is our incubation language around isolation and message passing, that is built on top of a variant of the CCR. So the question is, I'll actually make that two questions. Is there a mechanism in place to write your own scheduler? And could you then write your own scheduler to target, say, a GPU? The answer to the first question is absolutely. The answer to the second question is I think you'd have a very, very difficult time doing so. So there's a class called task scheduler, and I can derive from that. I can say my scheduler, which derives from task scheduler, and I can implement this guy. There are a couple key methods here. The main one is QTask, where basically when you have your own scheduler, the system just hands to you the task, and you can do whatever you want with it. There's also support here. I mentioned how we can reach into the queues, pull out a task, and potentially execute it in line. We call this method on the scheduler to do so. I'll also demonstrate that there's support for debugger integration, where the debugger is able to figure out what's in your queues and render really interesting information about that. You can support that on your own using get scheduled tasks. And there are some other methods here that are not abstract but virtual that I can override to do interesting things. The second portion of taking arbitrary delegates in .NET, which is basically what a task wraps, and running that on the GPU is a pretty difficult problem. It's one we're also looking at, but certainly doesn't show up here. The question is this the mechanism you would use to layer in prioritization of work? Yes, in .NET 4. We are looking at potentials in the future for having built-in support for prioritization, but there's currently nothing like that outside of writing your own scheduler. Yeah. Can we use UMS threads? UMS threads are user mode schedulable threads, not from the managed stack. We don't provide any support for it. The CLR itself could be used from UMS threads, but you can't, well, it would be ill-advised to write a user mode schedulable scheduler, UMS scheduler in managed code. You run into some significant issues around things like the garbage collector in terms of each wanting to be able to pause the world and control threads and so forth. If you are more interested in UMS, there are two great talks later this week, one by Dana Groff on how the concurrency runtime on the native stack takes advantage of UMS, and one by one of the developers on the Windows kernel team talking about the actual implementation of UMS. Can you replace the default task scheduler? In .NET 4, there's no way to just carte blanche say, anyone who is using the default scheduler to use something else. And we actually did that very specifically because people can take dependencies on the semantics of a scheduler, and we wouldn't want that ripped out under the covers. That's maybe something we change in the future. But for right now, you have to be very explicit about which scheduler you want particular tasks to target. That said, tasks run on whatever the current scheduler is. So if you create tasks from within other tasks and that outer task was created on a scheduler, the children or those subtasks will also run on that outer scheduler. So you could launch all of your work from within a task that was on a different scheduler, and unless overridden, then all that work would go to that other location. All right. Jump back to slides. So I didn't actually demo the concurrent collections, but I will point them out. I mentioned we have all these synchronization primitives that we've added in .NET 4, most of which came about because we actually needed them internally. It's sort of a laundry list here, so I won't walk through all of them. But you can get a sense for the amount of work that was done and the amount of new primitives that are available to you to use. Thread-safe scalable collections like a queue, a stack, a bag, and a dictionary. Blocking collection for producer-consumer. Support for lazy initialization both across the board and per thread. Some lower-level synchronization primitives. Support for a new mechanism for doing cooperative cancellation across huge swaths of asynchronous work. So there's lots of things here. We've actually started creating some Channel 9 videos on these. So if you're interested, go up and check out Channel 9. And you can look up some interesting information. We're also looking to revamp our Dev Center, our Parallel Computing Dev Center, to have a whole lot more information on these types. And I'll be happy to chat afterwards if people have any specific questions. All right. So the sort of the top level of the task parallel library is all about loops. Control flow loops are a very common form of work. In fact, the predominant form of work in most applications, whether it's a for loop or a for each loop or a sequence of statements. If, and this is a big if these loops have all iterations independent, or they've been made independent through your own synchronization, then you can parallelize them. So there's this new type, system.threading.tasks.parallel, where you can say parallel.for or parallel.foreach or parallel.invoke. And under the covers, as with plink, we'll handle processing this work with as much parallelism as we can possibly muster. Again, based on the underlying scheduler, which by default is the thread pool. Wherever possible, we've tried to maintain sequential semantics or serial semantics. So for example, with a typical for loop, like the one shown on the slide, we're not going to go beyond that for loop until you're done the work in the for loop, either successfully or exceptionally. The same thing is true with the parallel loops. So we try, you're not going to get to the location after that semicolon at the end there until all your work is actually complete. Or things have gone wrong and we've sort of quiesced the system and we rethrow the exceptions. There are a whole lot of knobs on these loops, which you can explore for how for things you can do with them, being able to cancel them, control degree of parallelism, specify your own custom partitioning if the partitioning we have out of the box isn't good enough for you, do your own scheduling, use task local state. There's a whole lot of stuff. On top of that, there's also support, which I'll show, for built into the Visual Studio 2010 profiler, where you can actually see where your loops were running. So let's actually take a look at that. Switch back over to my demo machine. That's not my demo machine. I'll bring up an example which some folks may have seen previously. This is a ray tracer. Ooh. Oh, right. It usually is best to have a main method instead of button one click. So I've got a little ray tracer here. This was originally written by Luke Hoban, who's the PM for the F# team. We have a little bouncy ball here. And this is being rendered in my ray tracer. Using a simple doubly nested loop. We've got 4 and 4. I can replace this outer for loop because all iterations of this outer for loop are independent. I can replace that outer loop with a parallel for. And now when I click this, again, magic parallel button, we're getting about 4x the frame rate, rendering each image about 4 times as fast. And you can see that instead of 1.0 or 1.1, we're getting about 3.9 or 4.0 frames per second. And I can actually see how the various threads are participating. Oh, some of the colors are very similar. Try that again. There we go. You can actually see how various threads are participating in the rendering of this image and how they're sharing work and partitioning. Again, if you don't like the partitioning we use by default, you can change it, but this is what you get out of the box. Now let me run this again, and this time I'm going to run it under the profiler that I alluded to, which is a new feature in 2010 that allows you to visualize the behavior of a multi-threaded application. So I will run this application again. I'll run it first sequentially, so about 1 frame per second. And now I'll run it again in parallel, about 3.8, 3.7 frames per second. And I'll let the profiler do its thing. So what just happened was, while I was running this application, the profiler asked the operating system to turn on something called ETW, or event tracing for Windows. This is basically a very lightweight tracing mechanism that's been plumbed throughout the Windows kernel as of Windows, or we're using functionality that's there as of Windows Vista, Windows Server 2008. That allows us to get detailed information on pretty much anything the kernel does. Now, we care about a few specific things. We care about things like context switches. We care about when threads block. We care about file and I/O reads and writes and so forth. So we asked the profiler to generate all that information, and now we're mining it, including loading up symbols from the Microsoft Public Symbol Server, to generate some detailed visualizations of what our application looks like. So here we can see my applications run. We have time on the x-axis and number of cores on the y-axis. And we can see that here's my sequential run using 1 core. And here's my parallel run, for the most part, using 4 cores, except for these little dips, which we could probably guess are where we were between frames and doing a little bit of sequential work to process each frame. If I want to get more information on that and to kind of verify my guess, I can switch over to the threads view. And now I can see all the threads in my application, including my main thread, which is my UI thread. And I can see exactly where all of my parallel loops were. I can see what they were doing over time. And I can even drill into very fine levels. For example, this is interesting. I've got a moment in time where all of my threads were paused while some threads down here were doing something. So I might want to know what that is. Click here, view the stack. And now I can see that I was actually blocked on a GC. So this is the garbage collector kicking in down here. And in fact, if I click here, I can see that the GC was doing a GC heap promote find first object. I don't know what that means. But nevertheless, you can get some really deep insights into the behavior of your application. And you can use this to find things that have gone wrong. So to your question earlier around knowing where things are running, I can see whether my work was running in the right place or not based on this trace that was generated. I would expect it to be running on these CLR worker threads, but I might see it on the main thread and instantly know there was a problem because I would see nothing happening in the background, lots of work happening in the UI wrapped by one of these parallel loops. There are some other examples of some key things you might see go wrong. Let me switch over to my profile examples project. And I will run this one under the profiler. So this is going to show me a few things. One, I've coded up some pretty poor code. One to show load imbalance, one to show oversubscription, and one to show a lock convoy. So load imbalance is where you've divvied up work to be processed by multiple threads. I've purposely gone out of my way here to screw up how parallel 4 works. Oversubscription is where you have too many threads, and so lots of context switching that's taking up a lot of time. And a lock convoy is where you have a big honkin' lock, and all your threads are basically serializing on that lock. So while you thought you were going parallel, you're actually still largely running sequential. So while this is running, I can bring up my bad code for that, just to highlight what we just ran. Here's my load imbalance. I'm using a type called partitioner, which is this kind of custom partitioning behavior, to actually specify a bad partitioning. I've got my oversubscription, where I'm creating a whole bunch of threads that are doing a lot of CPU-bound work, way more than I should really have. And I've got a lock convoy, which is a parallel 4, just continually synchronizing on a mutex. And if I go back and look at this in the profiler and sort by execution, first I can see my load imbalance. You can see I've got a bunch of threads here that were all part of this parallel loop. And I can see certain threads that were ending well before other threads. In the meantime, they're just sort of sitting there hanging out, waiting for their thread brethren to complete the loop so that they can go on and do other things. So you see a pattern like this, you know you're in trouble, you need to go fix something. I've got another example here. You'll notice there's very little work. In fact, there's all this preemption, yellow is preemption, where threads are just getting swapped out like crazy. And they're only doing a little bit of work, and then they go away. And in fact, I can see why they went away. In this case, it was because their quantum expired, and they were preempted by, in this case, service host, in this case, by system, in this case, by this actual application itself, one of the other threads, and so forth. So again, you get some deep insight. And here, with my lock convoy, I'll sort again. by execution. If we look up here, we can see my loop, where this green is just jumping around like crazy. Most of the time we spent blocked because we were actually synchronizing on this one synchronization mechanism. So you can get some very cool insights into your application from the profiler. I'll run this again under the debugger just to showcase some of the new debugging features. Let me get rid of load and bounce. And I'll show the lock convoy. So if I set a breakpoint in here, actually, I'm just going to run this and then break in. And if I look at my new parallel stacks window, I can see, let me zoom out a little bit, I can see all the threads in my application and everything they were doing. So I've got 3 threads, I have 7 threads in my application. 3 of them went up in this direction. One went here, one went there, one went up here. I can see exactly their call stack. When there were 4 threads that were all doing the same thing, all their call stacks were merged. So here in the debugger, in fact, I can actually visualize the fact that 4 of these threads are blocked on a lock, and only 1 of them has been able to continue on. I can also narrow this down just to focus on tasks. We've made task a first-class citizen in the debugger, and now you can see I've got 5 tasks, 4 of which are waiting on a wait handle, and 1 of which has made forward progress. We also have the new parallel tasks window, where I can see all of my tasks. And if I had scheduled tasks, we can actually see those as well. It'll reach into the scheduler's queues and show me exactly what was scheduled. So some really, really useful debugging functionality. There's a great article. Well, I don't want to say it's great because I was a co-author of it. There's an article on MSDN that Daniel Moth and myself wrote that went through several examples of where the parallel stacks and task window can help you find such problems. And Daniel also filmed a Channel 9 video, about 20 minutes, well worth your time, that videos those examples from the article and shows how useful these windows can be. This is about scheduling. Fun with loops. And there we are. All right. So a couple core messages. One, Manycore is here. And it's happened, and it's not something we can avoid. So it is something to start thinking about, whether you can upgrade to .NET 4 today or even in the next year. Definitely be thinking about how you can parallelize your applications, existing and new. And then there's a whole lot of things you can follow up on. Most of the examples I showed are actually available for download online. And most importantly, we do love feedback, whether on this session in particular or just in general on the work we're doing. So definitely let us know. You can go to us through the forums or our blogs. And of course, there are session evaluations as well. And I'd love any feedback you may have. Thanks a lot.